Hello folks, and welcome back to another lesson. Today we're going to be jumping into something entirely new. Section 7.3 deals with what we call logarithmic functions. Now to set the stage, let's look at this start thinking problem. We're asking how long will it take to get to $4,500 if you invest $3,000 in an account that pays 8% interest compounding continuously. So let's write out what we can for this equation. We're trying to get to an amount of $4,500. We started off with $3,000 and we put it into a compounding continuously function, so that's PE to the R, or 8%, T. Now if we're trying to solve for T here, best we can do right now is we divide by 3,000. When we divide by 3,000, we get 1.5 is equal to e to the 0.08 t. Now how would we solve for it at this point? We could guess and check, we could throw it into your calculator, but either way that's going to take some amount of work. So instead what we're going to be introducing is something called an inverse operation. And all an inverse operation is an operation that cancels out another. For example, multiplication and division, addition and subtraction. So the inverse operation of exponents is going to be logarithms. Or in other words, logarithms are the inverse of exponents So let's define a logarithm now. A logarithm, and we call these with base b, of a positive number x satisfies the following definition. We need our base b to be greater than 0 and not equal to 1. If we do that, we have log base b of x is equal to y. So that's the way we read this. Log base b of x is equal to y if and only if b to the y is equal to x. Or in other words, notice how our base b, is just the base of our exponent. So b is going to be the base of the logarithm, the bottom number in the logarithm, as well as the bottom number in the exponent. Also note that the number that the logarithm equals is the exponent. So the logarithm equals the exponent. Now this leads us to our main concept here. Logarithms are the same thing as exponents. Logarithms are exponents, exponents are logarithms. So we can switch in between the two interchangeably. Let's take a look at a practice problem of switching from exponents to logarithms, and then we'll have you practice a couple. So here we have 2 to the third is equal to 8. If we want to convert it into a logarithm, we take our base value here, the base of the exponent, and turn it into the base of our logarithm on the other side. So in other words, what this becomes is we have a log base 2, so we put the 2 underneath, and it'll be of 8. So we bring the logarithm to the other side, and that would be equal to 3. So how do we do this? We take the base of the exponent, make it the base of our logarithm, and move it to the other side. Now let's have you all try switching a couple around. We have 5 cubed is equal to 125. What is that as a logarithm? So for this, we make the 5, the base 5, our base of our logarithm. So we have log base 5, and then we bring it over to the right-hand side. So log base 5 of 125 is equal to 3. Okay. What about 6 squared is equal to 36? 6 squared is equal to 36. Our 6 becomes our base, because it's the base of our logarithm here, or of our exponent. And we have log base 6 of 36, the number on the right-hand side, is equal to our exponent. Remember, your equal will always be your exponent. Logarithm equals the power. One last one, 2 to the 4th is equal to 16. Write that as a logarithm. So for this, 2 is our base, so this is log base 2. And then we use the number on the right-hand side of 16 is equal to our exponent. So log base 2 of 16 is equal to our exponent. Okay, we can also do this in reverse. So we can go from logarithms to exponents. In this example, we have log base 3 of 9 is equal to 2. The base of our exponent, or the base of our logarithm, becomes the base of our exponent on the other side. So this becomes 3 squared is equal to 9. We take the base of the logarithm, make it the base of our exponent using the opposite number, and it'll be equal to the other side. Now let's have you all try a couple. What's log base 64? Log base 4 of 64 is equal to 3. How would we write that as an exponent? Now the base is 4, and we're going to move the 4 to be the base of the exponent on the other side. So this would become 4 to the 3rd is equal to 64. Okay. Log base 3 of 9 is equal to 2. How would we write that as an exponent? So the base is 3, we move the base over to the other side. It becomes our power, or our base of our exponent. So 3 squared is equal to 9. What about log base 10 of 1 is equal to 0? For this, we move the 10 to be our base of the exponent. 10 to the 0 is equal to 1. And so far, all of these are true. 3 squared is 9, 10 to the 0 is 1, 4 cubed is 64. Okay, so that's how we convert between the two. Now, how do we actually define or evaluate a logarithm without a calculator? Let's say you have log base 3 of 27, and we're trying to answer this. The way we do this is we're going to set this whole equation equal to some value, equal to x. And then we're just going to convert in between the two. So we're going to say log base 3 of 27 is equal to x. Well, we can move the base 3 to be the base of our exponent. And we have 3 to the x is equal to 27. And then here we have to do some work. We say 3 raised to what power is equal to 27? Well, it's not 0, because that would make it 1. 3 to the first would be 3. 3 squared would be 9. Our answer is that 3 cubed is equal to 27. So our answer for this equation is x is equal to 3. Or log base 3 of 27 is equal to 3. So that's the process for evaluating a logarithm. Set it equal to some variable. Move your logarithm to be an exponent. So convert your base into the base of the exponent, and then figure out what your value is. Hence we get log base 3 of 27 is equal to 3. Let's give you all a chance to do this. Let's have you solve or evaluate log base 5 of 125 by hand. What is this equal to? So first step, we're going to set this equal to x. Then we're going to bring the 5 over to the other side. So we get 5 to the x is equal to 125. And 5 to the x is equal to 125. What power of 5 gets us to 125? That would be 3, right? 5 cubed is equal to 125. So that means that the log base 5 of 125, right? That's the power that we're looking for. 5 raised to what power gives us 125? That's equal to 3. Let's try this next one. It's a little bit trickier, so don't be afraid if you get stuck. That's okay. But we're going to try log base 4 is equal to 32. The other way of reading this logarithm is saying 4 raised to what power gives us 32. Go ahead and give this a shot. If you can't get all the way to the answer, just write the step that you got down on, that you completed. So we set this equal to x. We get log base 4 of 32 is equal to x. Or this is saying 4 raised to the what power, the x power, is equal to 32. Now we don't know a power of 4 that is actually the 32nd power, or is equal to 32, right? 4 to the first power is 4. 4 squared is going to give us 16, and 4 cubed is going to give us 64. So 4 doesn't get this, but we have to do a little trick here. 4 is the same thing as 2 squared. So this is the same thing as 2 squared to the x, or 2 to the 2x is equal to 32. Right? So 2 to the 2x is equal to 32. Or in other words, 2 raised to what power is equal to 32? 2 to the 5th power. Right? So we need 2x to equal 5, because we need the 2 to the 5th power to be our answer. Or in other words, our answer for this is going to be 5 over 2. So our answer is x is equal to 5 over 2. Right, we have one last one here. We have log of 100. Now how are we supposed to solve this? We don't have a base of a logarithm. Anytime there's not an base, we're using what's called the common logarithm, or our base is going to be base 10. So anytime you don't see a base number here, it just reads log of some value, read that as log base 10 of something. Or in other words, this is the same thing as the log base 10 of 100. What is this going to be equal to? Go ahead and solve. Now to solve this, we're saying 10 raised to what power is equal to 100. Right? That's what this value is. 10 raised to what power is equal to 100. We can rewrite that by moving our base over as 10 to the x is equal to 100. And what does that tell us? 10 squared, right? Or 10 raised to the second power is 100. So log of 100 is going to be equal to 2. Now I just touched upon this, but if we don't have a value in the base, that's using the common logarithm. And all the common logarithm means is it's the logarithm with base 10. So anytime you don't see a value, you're going to use base 10. Okay, that's the basics of logarithms. Now let's try to graph one. How are we going to graph this? Well, we started off by explaining logarithms are the inverses of exponents. So if we look at the graph of an exponent, we can invert it to find a logarithm. And that's what we're going to do here. We're going to try to figure out the graph of log base 3 of x by using its inverse, which we know is going to be y is equal to 3 to the x. So we're going to start by looking at y is equal to 3 to the x. Let's take some values here, x and y. We'll go from -1 to 3. And so for y is equal to 3 to the x, 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. And 3 to the 3rd is 27. So let's go ahead and graph our original function, or its inverse, which is y is equal to 3 to the x. Right, this is the inverse of our logarithm, but that means we can use this to find the actual answer to the logarithm. We get something that looks like this. Now importantly, what is our domain and range of y is equal to 3 to the x? What's our domain, or our x values? Our x values keep going to the left and they keep going to the right. So our domain for this is going to be -infinity to +infinity. And what's our range going to be? Range is our y values. And it looks like our y values don't ever touch 0, right? We have an asymptote at y is equal to 0. So our range gets super close to 0 but never touches it. And it keeps going up. So the smallest it gets is almost 0. The largest it gets is infinity. Okay, that's our domain and range of y is equal to 3x. Now we know this is the inverse function. Y is equal to 3 to the x is the inverse function of y is equal to log base 3 of x. So let's flip our x and y values and get our values for this equation. Log base 3 of x. So this means that at 1/3, we're going to have a value of -1. At 1, we're going to have a value of 0. At 3, we'll have a value of 1. At 9, we'll have a value of 2. And at 27, we'll have a value of 3. So now it's time to put this equation in. At x is 1/3, we have a value of -1. At 1, we have 0. At 3, we get to 1. At 9, we get to 2. So our graph of log base 3 of x looks something like this. Okay? And looking at it, because we had an asymptote at x is equal to 0 for our original function, for our inverse, that's going to flip to y. So we're going to have an asymptote at the y-axis, meaning that our function will get closer and closer to x equaling 0, but it will never actually touch it. Now all we have to do to find the domain and range, since log base 3 of x is the inverse, all we do is we switch x and y, and we switch our domain and range. That means that our domain for y is equal to log base 3 of x is going to be the range of 3 to the x. So our domain is going to be 0 to infinity, and our range is going to be our domain. So our range is -infinity to +infinity. So we just flipped our domain and range of the inverse function to get to our values. Our domain is 0 to infinity. Our range is -infinity to +infinity. All right, let's have you all try doing one of these. Specifically, we're going to have you try to graph y is equal to log base 2 of x using its inverse function. What is its inverse function? Well, if you need help with that, we're going to flip this over. We're going to flip the base over, or the inverse is y is equal to 2 to the x. The inverse is going to be the power as opposed to the logarithm. So create your tables of values and try to graph these. To start off with, let's do our tables of values. For x and our inverse, or y is equal to 2 to the x, let's use values the same as we did before, so -1, 0, 1, 2, and 3. When we do that, y is equal to 2 to the -1, that would be 1/2. 2 to the 0 would be 1. We'd have 2, 2 squared is 4, and 2 cubed is 8. So our inverse function would look something like this: 3, 8. And our domain and range for this, domain, or our x values, goes all the way to the left and right. So our domain is -infinity to +infinity. Our range, or the y values, again, we have an asymptote at y is equal to 0. So it never actually hits 0, it just gets super close, and it goes all the way up to infinity. Our flipped values are going to be our inverse function, which is the logarithm, log base 2 of x. So that'll be 1/2 -1, 1, 0, 2, 1, 4, 2, and 3, 8. Right, we just flip our x and y values to get your inverse. So we'd end up with 1/2 -1, 1, 0, 2, 1, 4, 2, and 8, 3. And we'd end up with something looking like this. again, we have an asymptote at the y-axis, meaning it gets close to the y-axis but never touches. And then knowing our domain and range of the inverse were negative infinity to positive infinity, and our range was 0 to infinity, what is the domain and range of the logarithm going to be? For an inverse, we just flip the domain and range, just like we flipped x and y. So our domain for the logarithm would be the range of the inverse, or of the exponent. So our domain is going to be 0 to infinity, and our range is going to be the domain, negative infinity to positive infinity. And we'll write our domain and range back in here as well. Okay. So that's what a logarithm looks like. That's what the graph looks like. Just like with the rest of the functions we've been looking at, we can transform it. We can move it up and down, we can stretch it, we can move it left and right. In this case, the parent function, or the most basic form we're looking at, is y is equal to log base b of x. Now if we're doing reflections, stretches, and compressions, that's going to be the a value here. Reflections are going to be when a is a negative number, so when it's less than 0. Stretches are when the value of a is greater than 1, right? We want a to be larger than 1 so we can make it bigger. And compressions, just like always, are going to be a is a decimal or a fraction. Positive or negative doesn't matter because we're just talking stretching or compression. The negative just reflects it. And then translations, right? So we'll have log base b of x minus h. So inside of the logarithm, we'll have one value, and then k will be on the outside. H will still move us left and right, just like normal. And k will move us up and down. So the same thing we've been dealing with all year here. Let's do a couple of examples of this. We're trying to figure out how this function y is equal to negative 2 log base 4 of x minus 3 plus 1 differs from the parent function. We're also trying to figure out what the domain and range will be. So for this one, what's the parent function? The parent function is going to be just the log base b of x. So the parent function is log base 4 of x. 4 of x. So how does it differ? Well, we've reflected it and we've given it a vertical stretch of 2. And we have a vertical stretch of 2. The minus 3 is going to move us right 3. And the plus 1 is going to move us up 1. Let's not worry about the domain and range for these. Let's just look at these and have you do one of as well. We're trying to figure out how y is equal to 3 log base 5 of x plus 2 minus 3 has changed from its parent function. What's the parent function? It's just log base b of x, so it's log base 5 of x. Tell me all the ways this has changed from log base 5 of x. For this, the 3 means we're going to have a vertical stretch of 3. The plus 2 tells us we're going to move right by 2. And the minus 3 is going to move us down 3. And folks, that is your introduction to logarithms. Remember, logarithms are just exponents. We can use them in the same way, and we'll be dealing with some new rules for them upcoming in the future. Anyways, go ahead and get started on your work.